All right, so in this video, we're going to go over how to find Taylor series from other Taylor series we already know. So for example, we can start off with this example that's just listed on our slide to the left here. How can we get the Taylor series for sine of 2x cubed from the Taylor series we know for just sine? So if you remember, the Taylor series for sine of x is equal to the infinite sum from n equals 0 to infinity of minus 1 to the power of n times x to the 2n plus 1 power all over 2n plus 1 factorial. Remember, sine has all of the odd terms. So for us, what we can do is basically think of this as a composition of functions. So before we get carried away here, I want to say our overall goal here is really to figure out, you know what is sine of 2x cubed? And the spoiler is we're going to use the series we already know for sine to help us get the series for sine x cubed. So let's go ahead and do that. And the way in which we think about this is through this composition of functions, or basically this stenciling idea. Whereas wherever we had an x before in our equation, I'm going to surround that by some parenthesis. And the reason I do that is I'm going to take those x's out in a moment, and anywhere we have those parentheses, there's just no more x's inside. And the reason I want to do that is, well, whatever I put in those parentheses, I just put in the parentheses in both sides of this equation, in both the function itself, as well as inside of its Taylor series representation. So if we just had x's inside of those parentheses, we would just have the Taylor series or Maclaurin series for sine of x. But what we're interested in is the Taylor series for sine of 2x cubed. So inside of those parentheses, we can put those 2x cubes, and that gives us that Taylor series for sine of 2x cubed. And just to practice a little bit of algebra here, we can just expand sort of that right-hand side's power. So we still have minus 1 to the power of n. We have that 2n plus 1 factorial in the denominator. But in that numerator, since we have multiple terms all being raised to the same power, we could split that up into each of those individual terms raised to that power as well. So that means we could rewrite that numerator as a 2 to the 2n plus 1 power times an x cubed all raised to the 2n plus 1 power. And full disclosure here, the reason I'm going through these extra algebraic steps is just for us to practice some algebra. If you had an answer on a test that just said, hey, find the Taylor series for sine of 2x cubed, that would totally suffice unless we asked for further simplification. All right, so let's just continue with some of this algebra here. So we still have that minus 1 to the n. We can leave that as 2 to the 2n plus 1 power. And now we have this x cubed all raised to the 2n plus 1 power. We could rewrite this as x to the quantity 3 times 2n plus 1 power all over 2n plus 1 factorial. And while you might see where I'm going with this, we can just basically then distribute this 3 into that 2n plus 1, and that'll be sort of our last step that we'll go through here. So we really have in that numerator x to the 6n plus 3 all over 2n plus 1 factorial, and that is our series or Taylor series for sine of 2x cubed centered at 0, or our Maclaurin series. So we're still using that same composition of functions idea, or that same quote unquote stenciling idea that we've used previously in the power series unit. Let's do another couple examples here. So this next example will be another sine function, and this is sine of 2x. So remember, we start off with the series that we know for sine, from n equals 0 to infinity of minus 1 to the n of x to the 2n plus 1 all over 2n plus 1 factorial. Sine is, again, all of those odd terms. And what we really think about doing to make this kind of our stencil is everywhere there's an X, we surround that in our parentheses. And then the next step we could really do is just go inside of those parentheses and get rid of those X's. So now whatever we put inside of those parentheses, we have the series on the left and its corresponding Taylor series representation on the right. So we're just going to put a 2x inside of those parentheses because, again, that's the argument of sine that we want from the original function. And that would be our Taylor series or Maclaurin series for sine of 2x. And I'll spare you some of the details here, but of course we can do a little bit of simplification as well. Where now we have, well, 2 to the 2n plus 1, just like the previous problem. And now we just have an x to the 2n plus 1 as well. And that's all over 2n plus 1 factorial. And the reason I wanted to go through this example is just to kind of write out the first couple terms of this resulting Taylor series. So again, we're really doing this term by term. So the n equals 0 term, we think about first. When n equals 0, we get a -1 to the 0, so that's a 1. We get 2 to the 2n plus 1, which means a 2 to the first power. So we get a factor of 2. And then from that x to the 2n plus 1, we will also get a x to the first power. And in that denominator, we will get a 1 factorial. So maybe it's worthwhile writing all of that information down. Okay, so that's our n equals 1 term. Then we have plus, and we'll go over that's the n equals 0 term. We'll now do the n equals 1 term. So that means we get a -1 to the first power, which is a -1. So actually that plus sign is actually a minus sign. We get a 2 to the 2n plus 1, or a 2 to the 2 plus 1, which is a 2 cubed. Then we get an x cubed as well when we fill in n equals 1. And in that denominator, we get that 3 factorial. And we can keep going on term by term. So when n equals 2, we plug in that accordingly. So we get -1 squared, which is a +1. We'll get a 2 to the 2 times 2 plus 1, or a 2 to the 5th. We'll also get an x to the 5th power, all over 5 factorial, and so on and so forth. So that is our Taylor series for sine of 2x. And you might be wondering, well, why are we actually going through some of those details? And well, the reason is, I want us to start thinking about what if we multiply some of these Taylor series together? Can we get the functions Taylor series for that product? So maybe let's make this a little more crystal clear here. So I have a function that's defined as, say, sine of x times cosine of x. And let's actually put a coefficient of 2 out in front. So this is the function we want to find its Taylor series for. So we have 2 options, really. The first option is we use that Taylor series recipe, like we did to actually derive the Taylor series for sine, cosine, the exponential, and all of those. The second option is use the Taylor series we already know. And for this type of problem, what I really care about is, let's find the first 3 non-zero terms of the resulting Taylor series. So what that means is we're looking at more or less an expansion like this. We're looking at some summation of individual terms rather than a total summation like the series compact form up above. So how can we actually do this? Well, let's remember some of the Taylor series. We start off with sine of x. And the first couple terms of the Taylor series for sine of x are x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so forth, x to the 7 over 7 factorial. And we could really keep going if we want. Remember, sine has all of those even terms, whereas cosine, sine has all the odd terms. Cosine has all the even terms. So cosine would be 1, minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. All right, why are we going with this? Well, we have our function that we're interested in finding its Taylor series representation, or its first 3 terms of its Taylor series, is 2 times sine times cosine. Well, we know the Taylor series for sine, and we know the Taylor series for cosine. We can just plug in the right-hand sides into both sine and cosine in this series function and distribute the terms and figure out the resulting Taylor series terms. Let's just go through that process. Again, we're just interested here to find the first 3 non-zero terms. So we have that coefficient of 2 out in front. The first thing I'm going to do is write the first couple terms of our sine series. So let's go x minus, say, x cubed over 3 factorial, plus x to the 5th over 5 factorial. And if we need more terms, we can always add them later. And then we have the series for cosine. In the first couple terms of that series, 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial. And again, we could add more terms if we need them later on. So this thing on the right, or the left, excuse me, is sine of x again. This thing on the left, or the right, is cosine of x. And we're just going to multiply all of their terms out. And the resulting product, once we simplify it, will actually be the Taylor series for 2 times sine times cosine. All right, so let's go about and start doing this. And the way in which I like doing this is basically asking myself, what types of things can I multiply in these 2 series to give me constants? What terms can I multiply to give me just x to the 1st? What terms can I multiply to get x squareds? And so on and so forth. So if we take any term in this first series and try to multiply into any term in the second series, are we able to get anything with a constant? Well, let's take a look at this. We have this constant of 1 in that second series, but if we multiply that into any term in that first series, we're always going to have an x. So it looks like there's no constants in this resulting Taylor series. So we can ask ourselves, well, what terms in the first series and second series can we multiply then to get x to the power of 1? So maybe instead of doing this, we can just start listing the terms. So for example, what terms will give us constants? And it turns out there are none. So what terms in the series can we multiply to get x to the first powers? And let's take a look at this. We can take this x, and then we can multiply onto this 1 from the second series. And that gives us an x times 1. Are there any other terms we can multiply? If there are, we could just add them on here, but it doesn't look like there's any other terms for us to multiply that can give us just x to the power of 1 stuff. So the only x to the first terms look like, well, it's actually just x. So okay, let's mosey on along here. Let's ask ourselves, what terms can we multiply from the first series and second series to give us x squared type terms? And well, if we take any term in the first series like this x, and we multiply into anything in that second series, we're always going to get an odd power. So it doesn't look like we're going to be able to get any x squared terms when we multiply all these terms out. If we took the next term, which is this x cubed, well, if we multiply into anything in that second series, we already have a higher power than x squared. So it looks like there are none in terms of x squared terms. All right, so the next one we would look for are the x cubed terms. And well, what can we multiply from the first and second series to give us x cubed? Well, we can take this x, and I can multiply it onto this x squared over 2 factorial. All right, so let's write that term down. So we get an x times negative x squared, in fact, over 2 factorial, because that negative sign out in front there. And what other terms do we have? Well, I could take this negative x cubed over 3 factorial and then multiply it into this 1. And that'll give us another x cubed highest power. So what this looks like is, well, this is plus negative x cubed over 3 factorial, all times a1. And if we add all of these terms together, we'll get a negative x cubed over 2, and then we get a negative x cubed all over 6. So altogether, if we find common denominators, we would see that, well, this gives us a -4. Or let's actually just do the common denominators. So we get this is a minus 3x squared or x cubed all over 6 minus x cubed all over 6, which gives us a minus 4x cubed all over 6, which we could equivalently write if we really wanted to keep factorials in that denominator. What this really looks like is, well, a -4 all over 3 factorial times x cubed. All right, so it looks like we found the x cubed term of our Taylor series for 2 times sine times cosine. All right, let's keep going through this series together. All right, so the next thing we would look for are the x to the 4th terms. And well, again, if we take anything in this first series and multiply it into that second series, we're only going to get odd power stuff. So there's no way we can get x to the 4th term. So there's no x to the 4th terms in that resulting Taylor series. So finally, let's ask ourselves about the x to the 5th terms. All right, how can we get x to the 5th? Well, I can take that first x and I can multiply it by positive x over, or x to the 4th over 4 factorial. What else can I do? Well, I can take this minus x cubed over 3 factorial, and I can multiply it by minus x squared over 2 factorial. All right, what's the last way we can get an x to the 5th highest power? Well, we can take that x to the 5th over 5 factorial and multiply it by that 1. And that's how we can get x to the power of 5 terms. All right, so let's just do a little bit of simplification here. So this first term, what we really have is an x to the 5th all over 4 factorial, or 24. This second term will have a negative times negative, so it's a resulting positive. And that's an x to the 5th over 3 factorial, which is 6, times 2 factorial, which is 2. So that is over 12. And finally, that last term is an x to the 5th over 5 factorial. So that's plus x to the 5th over 120. So if we're trying to find common denominators here, it looks like the common denominator would be a nice 120. So how can we get that, or not? Is it? Yes, a 120. So we can multiply this first series by a 5 over 5. So we get 5x to the 5th all over 120. We can get in that second term, multiplying it by 10 over 10. So we get a 10x to the 5th all over 120. And then finally, that last term, we have just plus, well, x to the 5th over 120. So all in all, what that x to the 5th term actually looks like for us in that Taylor series is 16 all over 120 x to the 5th. And if we really wanted to keep factorials, that is, well, we could write that as 16 over 5 factorial times x to the 5th. So let's write our resulting Taylor series for 2 times sine times cosine. And remember, we found the first 3 non-zero terms. So the last thing we really need to do is, since we just looked at, well, the product of sine of x times cosine of x, we've kind of all ignored this factor of 2 in front here. What we really found so far was that this is equal to this factor of 2, and then times all of the terms that we found were non-zero. So the first term being just that x. The second term being that minus 4 over 3 factorial times x cubed. And the last term that we found that was non-zero was that 16 over 5 factorial times x to the 5th. And of course, there are many, infinitely many more terms than this, but this looks like the first 3 non-zero terms of that resulting Taylor series. And in fact, let's just multiply that 2 in. So this is equal to 2x minus 8 over 3 factorial x cubed plus 32 over 5 factorial x to the 5th minus ... And well, the reason I wanted to bring this up is because we've actually already seen these terms today in this video, in fact. And where we've seen this already is actually the Taylor series for sine of 2x. So these 3 non-zero terms that we saw here are actually the same exact non-zero terms for that resulting Taylor series that we just found for 2 times sine times cosine. So why does that make sense? And well, just to make this crystal clear, we have that 2 to the 1st times x. Next, we have a 2 cubed x cubed all over 3 factorial, plus that 32 is actually a 2 to the 5th x to the 5th over 5 factorial. And then, of course, lots of other terms. And well, if you remember some trig identities, you might remember one of these trig identities is that sine of 2x is equal to 2 times sine of x times cosine of x. And what we just showed was, well, we found the Taylor series for sine of 2x just using sine. And well, we found the Taylor series for 2 times sine times cosine using both sine and cosine's Taylor series. And we basically saw that this equality is maintained even in their Taylor series. So if we have trig functions like we do here, the trig identities actually also are equal with their Taylor series representations.